Okay, so far here in lecture, what we've been covering are the overall processes. Now we're getting down a little bit into the nitty-gritty of pyrolysis and some of the thermochemical processes that go on. So we covered torrefication, we covered a little bit on pyrolysis, a little bit on gasification. Now let's get into this little section on pyrolysis. It says, the traditional slow pyrolysis process that reduces wood to charcoal wastes a great deal of energy. But the term pyrolysis is now normally applied to a process where the aim is to collect volatile components and condense them to produce a liquid fuel or bio-oil. We're working on getting a pyrolysis unit at St. Pat's here, and so they would actually use some of the heat energy that we just talked about being wasted, hook it in with their HVAC system, and now they're not burning non-renewable natural gas. They're just using their waste as an energy thing right at the source, and not paying the tipping fees to have stuff hauled all over the place and stuck in the landfill. Another one, it says variation on the basic process include solvanolysis, the use of organic solvents. So there's more chemistry rather than just pure thermal at 200 to 300 C to dissolve the solids into an oil-like process, and fast pyrolysis requiring temperatures of 500 to 1300 and high pressures. It says fast pyrolysis with the capture of the volatiles is used in the production of commercial charcoal. But as of this writing, pyrolysis processes for liquid fuel production are mostly at the pilot or demonstration stage. Okay, now gasification specifically is taking a solid fuel and turning it into a gaseous process. It's not new. Coal gas and town gas have been in use for decades. Wood gas as well for heating. So you're basically, similar to the distillation process where something's getting hot, the volatiles come off, and then they're more or less oxidized, burned. Producer gas is mentioned. It can be 3 to 5 megajoules per cubic meter. Not very energy dense, nowhere near hydrogen, but again, they're talking about converting waste into some kind of energy. And a lot of times the renewable energy sector in general is doing exactly that. It's taking waste. And you might argue, well, gosh, coal and oil and natural gas are just waste too, really old wasted biomass. But this is more like what's sort of being wasted here and now. Okay, let's take a look at what water gas. It says the basic low temperature gasification, so again, solid to gas, might leave a residue of char, mostly carbon, not a bad thing, similar to coal. This can also then be gasified by burning it at a very high temperature and injecting steam. So you're actually putting H2O into the process. You're sort of injecting liquid oxygen and hydrogen. Kind of cool. This temperature is sufficient to break the steam into hydrogen and oxygen. So another way to do it, obviously, is with electrolysis. Our hydrogen fueling station is an example of that low temp. But if you get it hot enough, you're sort of not only burning water, you're sort of unburning water. You're blasting that bond apart. So producing a mixture of carbon monoxide. So the carbon obviously is coming from that char. The oxygen is coming from the water. Hydrogen, obviously coming from the water, and then nitrogen, because in that steam there's nitrogen in the carrier fluid. There's kind of nitrogen everywhere, if you will. So this is known as water gas. Just making gas from water. So now you've got a nice source of hydrogen that can be used for a wide variety of things, and also the carbon monoxide. Okay, and this is a complete industrial gasification process using oxygen can produce a stream of carbon monoxide and hydrogen, as we just mentioned, with any other impurities such as tars, ammonia, and sulfur compounds being chemically removed. This is known as synthesis gas or syngas. So taking out the sulfurs, the ammonias, and the sticky tars. So it says from syngas, almost any hydrocarbon compound can be synthesized. So you've kind of got this nice gaseous ball now, and now you're going to turn it into a liquid. Might seem a little counterproductive, but sort of breaking it down to its building blocks, you can now engineer the type of liquid fuel that you might desire. Methanol is mentioned. And then finally, the Fischer-Tropsch process, named after the chemists who developed it in the 1920s. The two components, so we're looking at two components. Oh shoot, I gotta. Let's just look at the Fischer-Tropsch, because I don't think they've got the chemical formula here. Let's just look at the PCH. Let's just see if we can look at the actual chemistry. It always makes a lot more sense to me if I look at the chemical reaction. Okay, so it's not one specific reaction, but you can sort of see this might be, the water gas comes on, so you've got some pure hydrogen in there, you've got your carbon monoxide, and so depending on the specifics, you're going to have, so this could be methane, right? So CH4 is just methane, and then water coming off as well. So it's not one particular chemistry, but this is the foundation of it. So hydrogen and carbon monoxide. And sort of building that up into a longer hydrocarbon. So there's your carbon-carbon bonds. And I've always been under the impression that some of this then goes into agricultural products, so like ammonia, but I'm not seeing the nitrogen here that I kind of expected to see. Let's see if nitrogen ever comes into the equation. Temperature rises high. Okay. Reaction. So it gets fairly complicated, but products, hydrocarbons, oxalic, catalyst, cobalt. Yeah, so All right. Well, I think I might have just been mistaken. I could have sworn there was some kind of nitrogen involved, and then you end up with some agricultural product. But there might be some subtleties there that I'm just not fully aware of. Okay. So that is more or less the thermochemistry. Here's a shot. Nothing too major here. Just having gaseous fuel coming in. There's going to be some carbon there. Obviously, the air's got the oxygen, and then you're just kind of back to your regular old power plant with these guys. Biofuel is mentioned, of course. So going back, this is going to be either an alcohol-based product or some kind of biodiesel, which is more of an oil-based product. Variety of those. The next section, 4.9, talks about biochemical processing. So rather than something getting hot, all the hot processes we've talked about to this point, these are more just sort of room temperature. These are temperatures where organisms can actually survive and do their thing. And sometimes, if they're not regulated properly, they can sort of get out of control. I mean, I've seen actual, compost pile. You've heard of them catching fire or whatever because the heat, they just get so hot they sort of spontaneously combust. But if done properly, they stay wet and moist so that the delicate biochemistry can happen. What we're looking at here is a on-farm digestion plant in Scotland, similar to Hull's Dairy, like I mentioned. In fact, I think a lot of the equipment in Hull's Dairy was imported from this part of the country, Scotland and Ireland. Okay. Next in the book, we're looking at small-scale biomass plant, and again, you just have organisms inside using their long-evolved enzymes, and I'll show you an example of that shortly on the talk that I gave last week. And it's extraordinarily like you could not engineer an organism to do this. You're sort of extracting something that's already sitting there in nature and exploiting it to make these gases. So to my knowledge, I'm sure it's happening in some lab somewhere, but somebody's working on some engineering project to be more efficient than what they've just sort of got going here at this modest little plant. Okay. So this is landfill gas, showing what sort of comes off initially. So initially some oxygen's coming off, some nitrogen's coming off. Over the course of years, once these things get set up, you just got a big kind of methane mess coming off the thing. You can see here if the landfill's been engineered, you can sort of get the gases off if it's been capped, and this whole thing is just sort of consuming itself. I mean, it's alive. You're not going to find any place on planet Earth where there's not something trying to eat something else. And it just takes one little bug to get its colony going. So there's a lot of very complex biochemistry going on in here. So what do you think about it? All right. Here's another example of how you might take municipal solid waste and really take everything out of it. I don't want to get into the whole system, but you can see it can become very complicated. There were some attempts in Pennsylvania when I was living there to do something similar to this in near Harrisburg, and it failed. It fell through. They didn't really have all of their ducks in a row, if you will, and unless the whole system is kind of functioning, none of it functions. So it's not going to pretend that this is easy. I mean, it's a big technical challenge. Okay, sugarcane, again, a purpose-grown energy crop, and then a Brazilian ethanol production plant. So again, you're relying on a biochemical process, in this case, yeast making ethanol, more or less, as its own waste product for a biofuel. The next section is enzymatic conversion, and that's, an enzyme is just a fancy word for a protein that actually takes one larger molecule and converts it to a smaller one that can then be used in a thermal process. Okay, here's ethanol production from straw. So you can see right here is your enzymatic hydrolysis, the water coming off, distillation happening, that water then going to help keep the fermentation on track. The CO2 storage, kind of interesting, but you could sort of see like, gosh, maybe you could actually make this thing carbon negative. The storage itself has to come from somewhere. In an ideal world, the pumps themselves are run with solar or wind. Something that's kind of running there and driving the pumps. And off comes food, for molasses, and then ethanol for fuel. So you kind of got your biology over here and your technology over here. All right. And then a lot of people have been, working on this sort of zero waste life cycle analysis. We've been in my other course. We've been working our way through this book called Cradle to Cradle. So this is sort of a biological equivalent of that, if you will. And in my mind, you look at this thing, and it's a representation of the first law of thermodynamics. Energy and matter are not created or destroyed, and in every case here, there's some, one process is feeding another one. So all of the different things we've been talking about up to this point, have some outlet. These are the tough ones, the policy and the economic incentive. I'm dealing with that right now in a biomass project where we're looking at bringing woody biomass out of the woods at $100 a ton versus the coal that we're currently selling at $15 a ton. So if you sort of say, hey, our new policy is that we're going to keep the coal in the ground, save it for future generations instead of burning it up right now, that becomes policy, which can in fact make an economic incentive for the renewables to come in, the biomasses to actually compete rather than the slash burning and all that kind of nonsense. If we look, table 4.5 shows net life cycle gaseous emissions. So what's coming off in terms of CO2, SOx, and NOx. The coal-fired power plant industry has really done a pretty amazing job, you might admit, at keeping the SOx and NOx out of the atmosphere. And when I was at the Clean Coal Conference there in Billings a month or so ago, they said, well, if we need to, solve the CO2 problem, we'll do that too. And really, it's gonna take a lot of teamwork from a lot of people to make that happen. But I'm optimistic. Okay. There's a few other things. Range of fuel energy ratios. This is table 4.6, sort of showing that in all of these systems, depending on how much water is there, how much oil is there, how much cellulose, etc., there's going to be a range of how much energy you're likely to get off of these different systems. Miscanthus, they've sort of shown for combustion it's fairly constant, and for gasification it's also fairly constant as well. Okay. Economics is also given in 4.7, and we're sort of looking at the retail costs, and it's given in pennies per kilowatt hour. That seems like an old number, man. 3.5 pence per kilowatt hour. That's pretty cheap. That must be, let's see, the fossil fuel prices paid by large consumers are directly related to bulk. So this is sort of before the ratepayer pays it. This is just sort of what the utility is paying to get that energy out of the ground. You can see that electricity, of course, is more expensive because of all the technology and machinery that has to go into creating it. And these numbers are relatively old, so there's new numbers coming online. Cost of production at 7 Midwest corn ethanol plants. You can see that some of these guys are acting at a loss. But they've sort of broken it down. They've broken it down in terms of what it costs for electricity coming in, natural gas, and the chemicals, the labor. I'm always surprised how little the labor and management costs, as well as the maintenance and repair. Okay, and then finally, here's sort of estimates for the potential contributions from biomass, and this is going to be a good segue into the last little bit I want to show you here. And these are a lot of different studies. Each one of these bars is just another paper out there in the literature, someone's estimate as to how much bioenergy is actually extractable. You can see some of them don't include waste at all. There's no blue in that 2050 estimate. So these are just different authors' opinions as to where bioenergy will be. You can see that it's in petajoules per year. Fairly modest estimate. I mean, this is only 1 exajoule right here, and 1 exajoule is only 1/500th of our total global energy budget. Okay, so with that, I'm going to take a break, and then I want to get into our summary 2 paper. It's fairly pressing and important, so let's just take a...
It was an interesting paper.
Yeah, it's something, isn't it? It was, my friend Steve Corrick sent it to me. It was a little mind-blowing to look at.
I really had to look at other resources
Yeah.
and go through the references
Yeah.
to be like, is it really?
Yeah.
Really?
Yeah.
Negative outlook.
Really? Yeah, it's...
Like, whoa,
Yeah.
you need to chill out.
I mean, there's a lot of truth to what they're saying.